Hey, Algebra 1, we're in section 12.1 today, and we're going to be talking about inverse variation. So the idea about inverse variation is going to be better understood if you remember direct variation.
Come later. What I want you to know is that direct variation is very similar to this, except the B thing isn't there. So direct variation is defined as a relationship between two variables where one variable is equal to K times another variable.
Okay, that was from like lesson 5.2 a very, very long time ago. But direct variation describes this relationship here where y and x are said to vary directly, okay? Because there's this variable here, k, which we call a variable of the constant of variation, all right? And we talked about this before. Inverse variation is going to be different. With inverse variation, you notice you have y is equal to k over x, which is completely different. So it's an inverse relationship. It's not this direct, nice, all on one line relationship. It's this inverse relationship where one seems to be like the reciprocal of the other in a way. So I am going to highlight, let me go ahead and highlight this the way we did the last one. So here we see that our k value is up here, our x value is down here, and our y value is over here. So I want you to see the difference between them, and I also want you to make sure you understand how it works out. And then finally, the product rule takes into account the idea that if you have, let's say, 2 points that varies inversely, and so let's say those points are say x sub 1, y sub 1, and x sub 2, y sub 2. And so by this definition, you know that y sub 1 is equal to some k over x sub 1, and y sub 2 is equal to some k over x sub 2. Stay with me. I know this is a little weird, right? But what we know is let's say this is the same k because both of these vary in the same way. So we're dealing with the same k value in both of these cases. We know that we could solve for k by multiplying both sides of the equation by x sub 1, right? So x sub 1 here, swoop delicious, that goes away. X sub 1 here, you have this product. So you've got x sub 1, y sub 1 is equal to k. Similarly, you could do the same thing on this side. We're getting to the rule, I promise, I promise, I promise. So x sub 2, y sub 2 is equal to k on this side. Well, notice, if this is equal to the same k and this is equal to the same k, that means that these two guys are equal. So the product rule says that if you have 2 points that vary directly, very inversely, I'm sorry, please forgive me if I said very directly before, but we're talking about inverse variation, very inversely in the same manner, then you know the product of those two variables would be equal. You saw the math, how we did that? That was if they vary in the same way, if they're like a part of the same indirect variation. All right, or inverse variation, not indirect. All right, so that's the product rule. The product rule basically says if you know that these 2 points vary inversely, have an inverse variation, and the k value is the same, then x sub 1 times y sub 1 is equal to x sub 2 times y sub 2. All right. So we've reached our first example. Example 1, it says graph an inverse variation. So driving, the time it takes to travel to a certain distance varies inversely as the rate at which you travel. So this is not a direct variation, it's an inverse variation. So if you increase the rate, the time will decrease. If you decrease the rate, the time will increase. That makes sense in a way. So the equation r times t is equal to 250 can be used to represent a person driving 250 miles, needing to drive 250 miles. Complete the table and draw a graph of the relation. Okay, so let's go ahead. So this is kind of fun. If this person were driving 250 miles at a rate of 5 miles per hour, how many hours would it take them? Well, clearly we know that this is kind of like rate times time equals distance, not kind of like it is. Rate times time equals distance. If you wanted to find the time, you would do distance is equal to the time is equal to distance divided by the rate. So if we take 250 and we divide it by 5, we get 50. So it would take us 50 hours if we were driving at a rate of 5 miles per hour to get 250 miles. And so we'll continue by filling this in. Divide 250 by the rate, which is 10, we get 25. Divide 250 by the rate, which is 15, and we're going to get a number that I'm not going to think of right now. Let me do the easier ones, then I'll come back. Divide 250 by 20, you're going to get 12.5. Divide 250 by 25, you're going to get 10. Divide 250 by 30, that's a little hard for me. 40, 50, divide 250 by 50, just bear with me, chavalitos. And you're going to get 1, 2, 3, 4, 5. So I'm going to go ahead and get a calculator to give me the other values real quick. And there they are. And we can see, you know, as one increases, the other one decreases. Cool. And so now we're going to complete this table and we're going to draw a graph. So now we're going to draw a physical representation of this. Now, remember, direct variation was a straight line. Will this be a straight line, maybe in some other direction? What would this look like? Can you imagine? Before we get started graphing, I want you to think about it. Contemplate. So as you guys were contemplating, I was drawing this beautiful tiny graph. I hope you guys can see it. Okay, let's do X a little bit darker than that, and Y. So this is our X and Y. Really, actually, I should probably use the variables they gave us, right? I hear you talking to me. Yes, lady. All right, so across this X-axis, we have the rates, and across the Y-axis, we have the time that it would take, and that would be time in hours. And so now we're just going to plot these points. So at 5 miles per hour, it took me 50 hours to drive to that location. It'll take the person 10, we're down to 25. So that was a quick, rapid drop. 15, we're at 16. This doesn't look like a linear function to me. You see that? If it were like down here, I'd be happy, but no. Okay, so it's not linear. That's cool. 16 is going to be right around here. That's my guesstimation. 20 is at 12.5, so it's going to be right here. 25 is at 10. That's right here. 30 is at 8.3, so that's down here. 35, 7, 40, 6 point something. Let me get down here to 50. 50 is at 5. So I think I missed the mark, y'all. Let's put 5 here, and let's bring these other ones up. I think I drew some crazy stuff here. So this is our 5 is here. And something like this. So what we have is this kind of a graph. So what is this called? Well, I don't want to say what this is called before we see the whole thing, because we don't really see the whole graph. I don't mean that I need to put more numbers out here, because we get the idea. This is going quickly to 0. It's approaching 0. And let's think about this graph just really quickly before I go and graph it on Desmos. What I know is, like, the slower I go, the longer, the more hours it's going to take me. So the question is, like, if I did like 2.5 miles per hour, it would take me something like 100 hours, right? If I did really, really close, the hours would totally continue to increase, right? If I did 0, but wait a minute, 0 doesn't make any sense at all. I can't go 0 miles per hour and think that I'm going to get anywhere in any number of hours, infinitely number of hours. I just can't do it. And so what we have here is this graph is, it's a big word, is asymptotic to this line. I don't know if we talked about asymptotes before. I kind of think we have not. I'm surprised our text didn't put it as a vocabulary word, but it's asymptotic, right? It has an asymptotic relationship, because this curve of values that we're talking about can never actually cross or touch this line. And similarly here, it doesn't matter how, so this would be me increasing my speed, right? If I increase my speed, you know, as high as I want, I'm never going to make it there instantaneously. I'm never going to be there. It's never going to take me 0 hours to get there. And so again, this curve is asymptotic to this line here, the x-axis. So let's look at this a little bit more in depth. Okay, so I'm over here at Desmos, and I graphed x times y is equal to 250, and you see nothing here. And so that makes total sense, because I've got to zoom out a little bit, because remember, our graph was for large numbers. And so you can see at 50, right, at 50 miles an hour, it takes us 5 hours to get that. So this looks like the graph that I had. But the problem is, you guys didn't see this part. This is weird. And so I was hesitant to name this graph because you didn't see the whole graph. When you have equations that are varying, have this inverse variation, what you're going to find is that you're going to be graphing what we call a hyperbola. And I think of it a hyperbola because if I turn my head to the side as I'm doing now, you can't see me. I think of putting a line here and that's an H. And so this is a hyperbolic graph. This is a hyperbola. And so rational functions, which we're going to talk about, often have that relationship. I'm going to take this graph off just for a little bit of a moment and say, let's say y is equal to, because it looks like this isn't what we have, but y is equal to 250 divided by x. This is exactly the same graph, right? Because if you notice the x's here are just being kind of like multiplied together. The x and the y is being multiplied together. So this graph, this equation, y is equal to something over x, is called a rational function or a rational relationship. And we will investigate that a little bit more. So here in this example too, we're asked to graph an inverse variation, and they give us a little bit different information. They say graph an inverse variation in which y varies inversely as x and y is 15 when x is 6. So here, y equals k over x. That's the gold standard, or the form that we're going to use when we recognize we have inverse variation. So now we're just going to put the numbers in. 15, that's y, is equal to k over 6. 6 being x, and this is going to help us solve for k. We can find our k value this way. So I'm going to solve for k by multiplying both sides by 6, and then when I do that, 6 times 15 is 90. K has to be 90. What does this give me? Well, this gives me the generic equation of all points that vary inversely in this way. So y is equal to 90 over x. And you've seen us graph this before. This time I chose a really simplified table. I'm going to actually plug this into Desmos to get a better shape. But what I want you to see is that last time we only used positive values because we were talking about, when we did this example up here, we were talking about distances in miles per hour, so it didn't make sense to use negative numbers. But here, when we're just drawing the graph, we need to consider negative and positive numbers. So I threw some in here, negative 90 all the way up to positive 90, and I got these values. When I throw 0 in here, I can't divide by 0, so that makes sense that it's undefined. I'm going to plot those points. The computer wasn't happy with me graphing, so I took those points that I talked about and I plotted them down here on Desmos. And you can see we're getting that hyperbolic shape, dot, 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 and we can expect this to continue, this trend to continue in this way, and this trend to continue here. So we could add more points, or I could actually just put the equation in. Y is equal to 90 divided by x. And we see that it connects the dots, and we do indeed get a hyperbola or hyperbolic graph of this rational function. All right, so I'm going to do this last problem, and I might have to do a second video. Don't cry, it's awesome. We love math. Okay, if y varies inversely as x, so we know we're dealing with this. Let me get my pen on. Y equals k over x. If y varies inversely as x and y is equal to 4 when x is equal to 7, we're going to find x when this is the situation. We're not going to think about that now. The first thing we need to do is find our k value. And so what I'm going to do is solve for k by multiplying both sides by 7, and then I get that k is equal to 28. So the generic form of the equation that satisfies this situation is going to be y equals 28 over k. All right, so that's what we're dealing with. Now we're going to use that to get this. So it says find x. That's what we're, oh, this should be an x down here. Sorry, chavalitos. Sorry, mommy did bad thing. Okay, I'll make it nicer, I promise. Okay, so find x. That's what we're looking for when y is equal to 14. Not too bad. We're going to simply use this formula, put 14 here, 28 over x, and we're going to solve. Many ways to solve this. We can kind of do all kinds of things, but when I have a number in the denominator that I need in the numerator, I just flip it. Well, if I flip one side, I got to flip to the other, right? So I took the reciprocal of the right and take the reciprocal of the left, multiply both sides by 28, because I got to get 28 out of the denominator. I get 28 over 14 is equal to x. X, my friends, is equal to 2. And that's about all the time I have for this particular section right now. I will finish up in another video. Let me know if you have any questions. Take care, babies. Bye bye.